Yeah, welcome everybody to my inaugural lecture on categorification in functional analysis. And I'd like to start with a question, namely, what is the most significant concept in functional analysis? And since this is a recording, I can ask you, so I asked earlier today ChatGPT, and ChatGPT said the most important concept in functional analysis is the concept of a Banner space. And I'd like to push it even a little further and say the most important concept is the concept of space. And to explain to you what I mean, let me draw a little picture. So let's say we start out from a calculus perspective. Then in calculus, you usually consider single functions. Yeah, so let's say we have some function f, and then, for instance, you calculate the derivative. Okay. And if you move from here to functional analysis, then the major change in perspective is that you don't consider a single function, but you combine functions of a certain type in a space. So you consider a space of functions, and the process of calculating a derivative then becomes again a function between such spaces, or what you then call an operator. And if you like neologisms, you may call this here spacification. Okay. And if you do categorification, you do more or less the same thing again. So in category theory, you put together all spaces of a certain type into a category. And in the category is not only the spaces, there are also the structure-preserving maps called morphisms. So in this example here, this would be operators. And then you realize that things that you do in classic functional analysis, like calculating a dual space, is an operation from a category to a category, and these things are called functors. All right, so far about the picture. Now I'd like to start with the first section, and this is called applications. And since maybe some of you might later object that my applications are not that applied, let me put here speech marks just to be on the safe side. So now consider the space of C infinity functions over some open set omega and some linear partial differential operator from this space into itself. And then we ask the following question: can we solve the equation AU equals F in a way such that the solution U depends linearly and continuously on F? So for every F, we want to solve it, and the solution should depend linearly and continuously on the right-hand side. Okay, and in other words, we could say, does there exist an operator here in the other direction, which is a right inverse to this L. Yeah, meaning that if we first apply R to our F, it spits out a U, and if we then apply the LPDO to U, we get back the right-hand side. So this here should be the identity on C infinity. Okay, and now, of course, you see immediately that this can only work if the L here is surjective. So let's, for now, say L is surjective. And indeed, there are classic results that tell you when an L is surjective. And if this is so, then we can look at the following. So we take here our C infinity of omega and our surjective L. And now we form the kernel of this L and the inclusion. And here I write a 0 on both sides. And then you see that this is a short exact sequence of vector spaces, but it is also a topologically exact sequence. So topologically exact sequence of Fréchet spaces, because this here is the inclusion of a subspace, subspace topology. So you have here range equals kernel in as vector spaces and also as topological spaces. And the L is, because of the open mapping theorem, automatically open. And that's what is called topologically exact sequence of Fréchet spaces. Okay, and now let us abbreviate here these three spaces with x, y, and z. So these two also need not to be the same for what comes next. Okay, so what is next? Now we apply a functor to this sequence, and this is the hom functor with here a fixed e, and if you don't like hom, you can think just linear and continuous maps from e to whatever we put here. And then if you sub in here 0, you get 0, yeah? And then you get hom ex, hom ey, hom ez, and here you have post composition with k, here you have post composition with L. And if you look now at this, then this is again an exact sequence of abelian groups or of vector spaces. And so let's just check it. So here you need, in this spot, you need that this is injective, but since k is injective, this map here will also be injective. So now next up is this here. So here we need to see range equals kernel. So first, one inclusion, the range is contained in the kernel. That's just because the composition of these two there is 0. So we only need the other direction. And this is, of course, well known, but let's do it anyway, just for fun. So assume you have some G, which is in the kernel of this post composition with L. But then this is just a fancy way of saying if I compose G with our L, then this is 0. Now we look at the kernel. This was here this k, and this is also 0. And then the universal property of the kernel tells us this here will factor. So here is some morphism such that this here is commutative. And if you look at this, this just means you can write the G as something and then k. And that just means you are in the range of this map here. Yeah, so this implies the G is in the range of K composed with blank. Okay, so we have also here the this exactness property. So what about this spot here? Here we cannot talk about exactness because we don't have a map here, but we can grab into the homological algebra toolbox which tells us we can derive this functor here, then we get so-called x1, whatever that is, and we can extend the sequence here in an exact way and get here x1 ex, and then x1 ey, and so on. Okay, good. And this can be defined and calculated, but let's for now ignore that. But let's now assume, so let's put the E, so the E was arbitrary, so let's now put E equals Z, and then assume that this guy here is 0. So assume x1 Z x is 0. But then, due to the exactness, if this is 0, we get that this is surjective. So then this here, composition with L from hom zy to hom zz is surjective, but if this is surjective, we hit here the identity on Z, which means we find here some R from Z to Y such that L after R is the identity on Z. And that is what we were aiming for. Okay, so we can replace our question by a new question and ask, when is this x guy 0? And for this, there is an answer. So-called Vogt-Wagner splitting theorem from 1977, which says, yes, this is 0 if Z is nuclear and has a property dn, and X has property omega. Dn and omega are properties defined in terms of the seminorms of a Fréchet space. So this is quantifiers and estimates that can be checked in a concrete situation. All right, now I have a confession to make. Because I used here the C infinity of omega, since it's a nice space and I could nicely explain this here, but in fact C infinity of omega does not have this dn property, so we cannot apply this to the situation I sketched here, but there are other spaces of C infinity functions with different topology where you can apply this result. Yeah, so this method works for other Fréchet spaces of C infinity functions. Okay. Second part of the remark, instead of using considering an LPDO, you can also apply this method, and here now I'm not cheating, yeah, to the following situation. So say you have C infinity functions on a compact, then you can ask the question, can you extend these functions in a linear and continuous way to functions on the whole space? Yeah? And for this, you look at C infinity of Rn, and then you consider the restriction to C infinity of k, and ask, is here a right inverse of this restriction, which is then an extension operator. And here it's like this. If this has the n, can be characterized in terms of the geometry of this set K, and the kernel always has omega. So you can really answer this question here in this case. Yeah, and just an example. So say you have here some set K with a cusp. Yeah, then there are results that say if this cusp is polynomially sharp, then this space has property dn, and if this is exponentially sharp, then it doesn't. Yeah? And I refer here to a paper by Leonhard Frerich from 2007. There are also many references in this paper to work that has been done before in this direction. Okay, 3. If you consider a partial differential operator, you can not only ask if the solution depends continuously on the right-hand side, you can consider operators that depend on a parameter and then ask, if the operator depends nicely on this parameter, does the solution then also depend nicely on the parameter? So this is parameter dependence. And this you can solve also by considering a derived functor, but there you have to derive the tensor product, not the Hom functor. And there is a series of papers by Bonnet and Domansky on this topic from 2006 to 2010. Okay, and last remark, let's go back to this surjectivity question, and let's now consider something with constant coefficients, and let's not take a Fréchet space, but let's take distributions here. And then you can ask, is this surjective? And this was in fact the starting point for these homological methods. So it goes back to Palamudov, who considered in the 70s the derived functor of the projective limit functor. So this space here is a projective limit. So you consider there the derived functor of this, and then you can solve these kind of problems. Yeah, and if you want to see a modern exposition, then I recommend the book by Jochen Wenkenroth from 2003. All right, so that was my application section and also a little bit of history. And now I would like to tell you what I'm interested in. And these are so-called LB spaces. So chapter 2, LB spaces. And we are at definition 5. So what is an LB space? We consider a vector space X together with a topology tau. And this is an LB space if there exists a so-called spectrum of Banach spaces. So we have some Banach space x1 and then some continuous linear injection into a Banach space x2 and so on, such that three things hold. First, this vector space here is the union of these xn's. Secondly, the topology tau is the finest linear topology such that the inclusions of the xn's into X all become continuous. And third condition, the tau should be a Hausdorff topology. Okay, and if this is the case, we write x equals int xn. Yeah, and this is a so-called inductive limit or co-limit. And now you see where the AB stands for, L for limit and B for Banach spaces. Okay, 6, some examples. So first example, consider the space of continuous functions with compact support on an open set omega. Then you can topologize this by taking continuous functions on omega but support in some compact set Kn, and the compact sets Kn you choose to be a compact exhaustion of your omega, and then you get here an AB space. And of course, you know, if I put here infinity, then this is the space of test functions. So let me call this here the little brother of test functions. Test functions would be an LF space because you get here already Frichet. Okay, second example, so-called Köther coechelon space. So we take AP spaces, and into the summation or supremum, we smuggle some weight functions, so some positive numbers. And then we take, so this is a sequence, and then we take a sequence of sequences that is decreasing, so that if we pass here from an to an plus 1, the space will become larger, and then this is the union and endowed with the corresponding topology. And this is called coechelon space. Okay, and third example, this trick here with using some weights. You can not do only with sequences, you can do this also with continuous functions or holomorphic functions. And I write down this holomorphic situation. So we take holomorphic functions on some suitable G, and then we again smuggle in some strictly positive continuous weight function and take the sequence of these decreasing, and then again we take here union and corresponding topology. And this is called a weighted space of holomorphic functions. Okay, so far I only told you the definition. So let's look at some properties that these AB spaces might have. And in fact, one reason why they are so interesting is that they might behave very badly. So we consider such a AB space X, and the first thing that you may hope is, since these xn's are complete, the limit space X maybe is also always complete, but this is in general wrong. So it is a property that this X can have or not. And for completeness, let me write it down. So X is complete if every Cauchy filter converges. All right. Then the next thing you can look at are bounded sets, also often very important. And then it's clear if you have a bounded set in Xn, in some Xn, then it will also be bounded in X. And the hope would be that these are all bounded sets in X. But in general, that's not true. And if it is true, we call the space regular. So regular if for every B in X bounded, then there exists an N such that this B is contained in Xn and bounded in Xn means in the norm topology. Okay, now I left out here something in the middle, and this I want to fill in now. So another property is so-called Mackey completeness. So the space is Mackey complete if every local Cauchy sequence is locally convergent. And now I have to tell you what this local means. Local means this convergence happens in some normed space. So this means there exists a disk absolutely convex bounded set such that this sequence is in this space XB, which has as a vector space just the span of B, and as a norm it has the gauge functional of this B. And to explain what this is, let me draw a little picture. Let's say here's the origin, and this here is your B, and now you want to calculate this norm here of this point X. Then what you do is you blow up this set B by multiplying with positive scalars. So this is here maybe lambda B, and then you take the infimum over those lambdas such that this blown up B swallows the X. So this is the smallest lambda, if you want to say so, that you swallow the X. Okay. Yeah, and then in this, so this sequence needs to be in such a space and there with respect to this gauge functional, which is a norm, Cauchy or convergent. Okay, and now why did I write this here in the middle? Because it turns out that normal completeness is stronger than this Mackey completeness, and here it turns out that these two things are equivalent. So this property here about bounded sets is in fact a certain completeness property. Okay, and so far you can find all of this at the very beginning of Grothendieck's test, but what you cannot find, neither a proof nor the question, yeah, about the backwards implication at the top. Yeah, so remark, I write it like this. So if regular implies complete is open, and since these things were all explained in Grothendieck's test, this one can say that this is open since the 50s. And the question, if this holds or not, has been attributed to Grothendieck as well. So I write attributed to Grothendieck, in particular by my late supervisor Klaus Bierstedt. Okay, now this is obviously some hard problem that many clever people tried to solve and didn't succeed. So I will not attempt that. What I want to show you is now how one can categorify this problem. And I start with proposition 9, which is due to Derived Sieg from 2016, and some bits are also due to myself. So we now consider the category of AB spaces. Objects are AB spaces, morphisms are linear continuous maps. Then here inside we have the category of regular AB spaces, and inside this we have the category of complete AB spaces. And missing first part of the proposition says these three categories are additive. And I will tell you in a bit what that means. Second part of the definition of the proposition, the categories AB and AB reg are pre-abelian. Again, I will tell you in a sec what that means. And 3, the complete AB spaces are maybe not pre-abelian, but they are Cherubian. Okay, proof. So what means additive? Additive means the Hom sets are abelian groups. There we can make a check. The composition is bilinear. There we can also make a check. And finitary products exist in this category. And for this you have to look at the definition. If you have finitely many spaces which are of this type, countable inductive limit of Banach spaces, then you can see how to write down this for the product. So let's make here a check. Now, second, these two are pre-abelian. That means every morphism has a kernel and a co-kernel. And I want to emphasize here, having a kernel is defined, or what a kernel is defined in terms of a universal property, exactly the one that I used in the first paragraph. And if some map F, so we take now some map F, linear continuous, and say if we are here, these are two AB spaces, then the question, if this map has a kernel, does not only depend on F, it also depends on the category we take the kernel in, because in this universal property, firstly this kernel must exist in this category, and then we test it against all other morphisms, with this factorization property, and what all other morphisms are depends on in which category we are. Okay, so let's now go for this. And I will make here a little table. So here I write the category, here I write the kernel, and here I write the co-kernel. Okay. Okay, and let's, before we start, let's, as a little warm-up, do here Banach spaces or Fréchet spaces. And what is then the kernel of such a map? Well, it's the kernel as in linear algebra, and then we take the subspace topology on it, and then you can check that this universal property holds. what is the co-kernel? So there in linear algebra, you would do this. But we need that this becomes a Banach space or a Fouché space. And this will maybe here not work out because we need to mod out something closed. And it turns out if you close it, this here, then this is again a Banach space and it satisfies the universal property if you take here this usual locally convex quotient topology. Yeah. Okay, and for later use, let me call this here Q. Okay, now let's go to AB. And here we run already in a problem. So algebraically, it's like this, that this kernel must be the preimage of 0. But if you take the subspace topology, this might not be again of this AB type. However, you can easily guess here how this is fixed. Yeah? So we have these spaces xn that give us the space x, and then we can just intersect this here with every step. This will be again a Banach space with a norm of xn, and then we take the limit over these, and this might lead here to a strictly finer topology than the subspace topology. Therefore, I use here this flat symbol for this possibly finer topology. Okay, and here on that side we are lucky because one can show that a quotient of an AB space is again an AB space. Okay, now regular AB spaces. Here we are lucky on that side because if this X is regular, then you can in a straightforward way check that this here will also be regular. Here, however, it's like this, that it may happen that a quotient of a regular space is not regular. And so we need somehow to make this quotient here regular or approximate it in a suitable way by a regular space. And now it comes in handy that I explained to you earlier that regular is actually some completeness property. And for a completeness property, one has methods to do this. Yeah, like a completion for the normal completeness property, and something similar we need now to do here. So what is the co-kernel? So this is Q sharp, and this is defined in the following way. We first consider the completion of this Q, which might not be an AB space. Then inside we have our Q, and then we consider all Mackey complete spaces which contain the Q inside this Q hat. Yeah, Mackey complete. And then we intersect them, and this way we get somehow the smallest Mackey complete superspace of our Q, and this is then actually an AB space and Mackey complete and satisfies this universal property for the co-kernel. So this is some odd duck here. Yeah. Okay, now complete AB spaces, and here it gets now even worse. So this candidate is of course this one here, but if you make the topology finer, and in the subspace topology, this will be complete if X is complete, but if you now refine the topology, you might lose that completeness. So situation here is like this. If this space is complete, then this is the kernel. And if it's not complete, then the kernel doesn't exist. Yeah? And some further comment here. This looks like we know everything, but we don't know if this case here actually happens, yeah? Because if this would happen, yeah, then this space, so if this means this is not complete, and then this would be a space which is regular by this, but not complete. So this would solve question 8. So we can prove this here, but if this case here really happens, is unclear. Okay, and here it gets even worse. So here we need to make this somehow complete. So the candidate is a completion, but if you complete an AB space, it's not clear if it will be again AB. So if this is an AB space, then this is the co-kernel, and if it's not, then I don't know. So there could be something larger than the completion, or different than the completion, that satisfies the universal property, but it's unclear. Okay, so if you read the table until here, we are done with part 2 of the proof. AB rec have kernels, and so every morphism has a kernel and a co-kernel. So it remains to look at part 3. And what means Karoubian? Karoubian means every idempotent has a kernel. So we have some map like this between complete AB spaces. And then if you have this, then you can see that this kernel, but with the subspace topology of X, is a direct summand of X. And if this is a direct summand, you can show that then this topology here and the topology with this B are the same. So then we have this, but this is complete as a closed subspace of a complete space. So we are done. Okay. Good. That brings me now to the next section. And I hope I could convey to you in the first paragraph that short exact sequences are kind of an important tool. So the next paragraph is exact structures. And we start with definition 10, which is in this wording here due to Henrath, Quam, Van Roosmalen, and myself, but in a slightly different way had already been used by Bazzoni and Crivet in 2013. And we take now some additive category and then we first consider the following class. So we take all kernel co-kernel pairs, which means we take sequences of this form where F is a kernel of G and G is a co-kernel of F. And now in this class we take some subclass C, so we choose some class C, and the elements of this C are then called conflations. So these are pairs F, G. And if we have such a conflation, so something in here, we call the F inflation and the G deflation. And for the remainder of this definition, I need the deflations. So I write this here, deflation. Okay, and now this C is called deflation exact structure, or the pair of the category and C deflation exact category, if three axioms hold, are 0, for every object, this morphism here into 0 is a deflation. R1, deflations are stable under composition, and R2, deflations are stable under pullbacks. And this I should explain. So what is a pullback? So let's take our deflation, G, deflation, and then we take some arbitrary morphism, so some arbitrary linear continuous map. And a pullback of G along this T is some object or some space in these examples, and maps like this such that this commutes, and it is the best object that does that, in the sense if I take some other object and morphisms such that this also commutes, then it factors uniquely through my P. And the condition is now, if I have a deflation and then I can take an arbitrary T, then this P here exists, and this map here is again a deflation. Meaning this has a kernel and the corresponding pair, this one and the kernel, belong here to my C. And just some more comment, checking this for some C is then involves then analysis. So think of these complete AB spaces. Yeah, then what is the candidate for this P? So you take here the product, it's complete, and then you take the subspace of pairs where G of Y equals T of S. This is closed, so also complete. But then you have to make this flat here. And this might mean you lose the completeness. So if you want to check this, you need to show this is actually then still complete. And then you have to form this kernel, and you have to show the kernel also exists. And then you need to check that this pair is again in your class here. Yeah? So this involves analysis. Okay, I wasn't completely finished with the definition. This has a part 2. So this class C is called an exact structure if these axioms are 0 through R2 hold, and also the dual axioms. And I don't want to write this out now, but one more comment. Yeah, so this is a classic notion from the 70s due to Quillen, and this was invented as a generalization of the short exact sequence in an abelian category. And these axioms guarantee that that you can prove these theorems in your homological algebra toolbox. And it turns out if you drop half of the axioms, so this is this one-sided generalization of Quillen exact structures that we considered here, then it turns out that a lot of things, not everything, but a lot of things you can still do only with half of the axioms. Okay. So now examples 11. And let's first go to Banach spaces, respectively Fréchet spaces. And here this class C all contains all such composable pairs such that F is injective G is surjective, and we have this algebraic exactness condition, range equals kernel as vector spaces. And this alone here is called algebraic exactness. Let me write this. So if this holds, we say the sequence is algebraically exact, but then we have here an additional topological property, namely the F needs to be open onto its range, or relatively open, and the G needs to be open, but in this case here we can of course drop this last condition because it's automatic. And now you see this is what I called in paragraph 1 a topologically exact sequence, and therefore it's abbreviated often by E top. And this is actually an exact structure, and therefore, although Fréchet spaces are not abelian, you can still do a lot of the homological tools you can use. Yeah. Okay. Second, so this is due to HRKW, and some results are already contained in Derived. So we consider the LB spaces, and here you can again look at this C all, and then it turns out that in C all you have all pairs Fg such that this is algebraically exact, and this is the only condition, so no topological additional condition. However, this is now not an exact structure, but it's a deflation exact structure only. Okay, and in fact, it's even the maximal deflation exact structure on this category. Okay, then you can nevertheless look at this topologically exact sequences. So there you have here, of course, also algebraic exactness, but then you have this topological conditions, and let me write them here like this. Yeah, so if you take on the range the topology of y, yeah, then this should be the same as if you take this flattened topology, and this should hold as topological vector spaces. And this is actually an exact structure, but needs to be checked. Yeah, so you need to check these axioms here. So this is an exact structure. Okay, and I left again here some space because it turns out in between these two there is still another exact structure, the so-called maximal exact structure, and here you have all pairs algebraically exact, and you do not need that these two spaces here are equal as topological spaces. You only need that they have the same dual space. So I write it like this: f of x tau y dash equals to this dash as vector spaces, and this is again an exact structure, and they are all strictly contained in each other, And let me mention that these two correspond actually to classic conditions of subspaces of inductive limits. Yeah? This means that the space is a limit subspace, and this means that this space is well located in X. Okay, and I have a third example here that is as follows. If you take, so this is now due to myself, if you take the regular LB spaces, then you can again look at this C all, but there this C all is not even deflation exact, but it strictly contains the maximal deflation exact structure, which is then again the algebraically exact sequences. So it's still something you can nicely calculate with. Okay, so now the last chapter, 4, derived categories. And I cannot give a full definition here, but let me write down the following. So we consider a Karoubian category C, and on this we consider a deflation exact structure. And then the derived category of C endowed with that C is given by the following data. So first I tell you what are the objects. So the objects are complexes over C. So something like this. Two consecutive morphisms composed are 0, and they should be bounded in the sense that eventually on both sides you only have zeros. Yeah, bounded complexes. And then the morphisms so let's say you have here some other complex y minus 1, y naught, y1, and then the first guess what should be such a morphism is its morphism in all these degrees, and these squares here should commute. This is in fact the first step how to define the morphisms in the derived category. So now what are they? They are in fact fractions of such morphisms here. I write it like this: sigma to the minus 1 f, where a certain class of morphisms is made invertible, like you invert artificially stuff when you pass from Z to Q. Yeah, so where a certain class sigma C of morphisms is made invertible such that in this derived category homological properties of C are built in. Yeah? And so this is tricky and technical. Just an example. You remember these X groups, and in fact the X groups are now contained in the Hom sets of this derived category. So if you want to calculate some X, you take the hom in the derived category, you read z as a complex by filling up with zeros, and x the same, but x you have to shift by 1 to the left. And then this hom set here in the derived category gives you exactly this x functor. In this sense, homological properties are built into the derived category. Yeah? And considering the derived category is like passing to some higher homological invariant. So let me finish with a theorem. First bit is due to Henrad, Quam, van Roosmalen, and myself, and goes like this. For these LB spaces endowed with the 3 exact structures that you can still see there, the derived categories exist. So I can take here the topological ones, and I can take the maximal exact structure, and I can also take this maximal deflation exact structure on the same category. And then I get natural functors in between here, but none of these functors is an equivalence. So that means this derived category can see what short exact sequences I picked here. Okay, part 2. If we choose for C either E top, E max, or D max, then there exists a natural functor between derived category of LB com with one of these structures to derived category of LB rec with the same structure chosen here. And the question, if this is an equivalence, so this is unknown, yeah, so this is well defined. So you can ask the question, is it an equivalence or not? And you could say this is a categorification of this problem 8, or more specifically, you might call this a homologification. Okay. And third part, so if you take, instead of the classic derived category, the relative derived category, in the sense defined by Jan Stoviček and others, that means we take here also a com, and now we take D max, but not D max on here, but D max on all LB spaces, and we define this relative to this larger category LB with that structure. Then here is an equivalence of categories. If you do this like this, and that means that on a homological level, these two categories here are the same, or have the same homological algebra. And one comment for experts, so what does that mean here, this relative derived category? So this is usually defined by a Verdier quotient, yeah? And here you quotient out the acyclics with respect to C in this category, and here you quotient out those complexes which are acyclic, so which are in AB, where the objects are in AB common, but which are acyclic if you look at them in AB with respect to this structure. So that's the difference here. Okay, thank you very much.